Creep is one of those sneaky mechanical properties that doesn't show up in a quick test, but absolutely matters in the real world. It's slow, it's steady. If you ignore it, it wins. Here's the hook. Ever notice power lines sag more on hot afternoons? Or a plastic shelf that bows over months? That's creep. Permanent deformation of a material over time under a constant load, especially at elevated temperatures. Let me break it down into stages, because creep isn't random. It has different stages. Stage 1, primary creep. Right after the load is applied, strain increases fast, then the rate tapers off. The material is work hardening, resisting further deformation so the creep rate slows. Stage 2, secondary creep, also called steady state. This is the long, flat middle of the curve where the creep rate is roughly constant. Dislocations and recovery processes balance out. Engineers care a lot about this region because it often defines the usable life at a given stress and temperature. Stage 3, tertiary creep. Microcracks and voids start linking up. The cross-section effectively shrinks, and the strain rate accelerates to failure. If you've ever seen a ruptured pipe, or a blade that necked before breaking, that's tertiary creep calling time. So what factors influence the phenomenon of creep? Stress, temperature, time. Higher stress, faster creep. Higher temperature, much faster creep. Especially once you're above about 0.4 of a material's melting temperature in Kelvin. And of course, enough time turns small rates into big problems. Now, examples. Jet engines and turbine blades. Nickel superalloys live in brutal heat and stress. Designers use single crystal blades, directional solidification, thermal barrier coatings to slow creep, keeping blades from elongating and rubbing the casing. Power plants and refineries. Boiler tubes and headers can creep over years of high-temperature service. Engineers specify creep strength-enhanced ferritic steels. Track creep life with inspection intervals. Replace parts before tertiary onset. Power lines. Aluminum conductors creep more in hot weather. That's why utilities account for sag at temperature. Clearances under lines depend on it. Polymers and plastics. Even at room temperature, a loaded PLA 3D print can slowly droop on a dashboard. Use PETG or nylon. Add ribs. Reduce sustained loads to fight polymer creep. Bridges and concrete. Concrete creeps under sustained load. Designers anticipate long-term deflection with prestress, camber, and mix design. Electronics. Solder joints on circuit boards experience thermal cycles that creep and fatigue. Alloy selection and underfill reduce failures. How do I design against creep? Pick the right material. Higher melting temperature, solid solution strengthening, precipitation hardening. Lower the service temperature, insulate, cool, reduce heat soak. Reduce sustained stress. Bigger cross sections, share the load, add supports. Use creep data. Steady state creep rate, creep rupture curves, and the Larson-Miller parameter to predict life. Plan inspections to catch the shift into tertiary before it's too late. Here's the mindset shift. Strength isn't just how much right now. It's also how much, for how long, at what temperature. Creep is time making its move.